So the next thing we want to look at is pointer arithmetics. And when we talk about pointer arithmetics, we simply mean the shifting of the memory addresses of the variables. Now we know that pointers store the addresses of variables on the computer memory. So when we add 1 to the address, what we're simply doing is we are shifting the address to the right by 1 unit. Or if we add 2 or 3, then we are shifting it by those number of units respectively, right? And it's not entirely like integer arithmetics, right? It's kind of the same intuition but a little bit different, and see what we mean by that in a bit. So we'll go ahead and then create two variables. The first one is going to be of data type int, and we want to call it num1, and we want to store in there 8. Now the second one is going to be a long int. I'm using this particular data type for the sake because of this example. What we want to explain, it's kind of easier to explain with this. So we want to call this num2, and we are equating it to 9, right? So you might have asked, so what's the difference between int and long int? We've looked at this specific data types in a previous video, why we use them and why they are advantageous, and we compared signed to unsigned as well, right? So I'll just go ahead and then quickly recap on why I'm using this. So a long int explicitly tells the computer that create a larger room for this particular variable. Even though I'm storing in 9, it doesn't matter. As so far as I've used a long int, it tells the computer that this particular variable that I am creating needs a larger room to be reserved. But for this one, comparatively smaller room is required. And when we look at this, I saved this. This was the video titled More on Variables and Data Types, right? So you can easily check that out. Long ints, they occupy at least 64 bits, and that's 8 bytes, right? Because 8 bits make 1 byte, so 64 bits will be 8 bytes. So they occupy at least 8 bytes in the computer memory. But for signed ints or ints, that's what we mostly use to. Basically, we are declaring signed integers, but it's acceptable in the syntax to just use ints, right? And these store at least 16 bits, and that's 16 divided by 8 is 2, right? That's 2 bytes. That was a quick recap on that. So why we are doing this is we are telling the computer to explicitly create an amount of storage that we want for a particular variable, because we might expect it to store much space. With that said, let's go ahead and then create two pointers for these particular variables. So the first one is going to be int. We want to call it p1, and we are saying that it's going to store the address of num1. The second is to be a long int, a rather long name, and we're telling the computer that this is going to be the address of num2. Right, so far so good. So to kind of get this, let's see if we can print them out. So we print out p1 and use a tab, then print out p2 with a new line. We run this and we've got an error over here. It says that expected and qualified ID before that. Okay, so I did not put in the p2, right? So I should put in the identifier of, or the name of the pointer. So we run this, we should not be getting any error now. And now we've gotten two addresses. It's working perfectly. Now what I want to do is to add 1 to it so that we can see the shift real time. So what I want to do is I want to say this is p plus plus p1, and then copy. Let's add some text as well. So let's say this is the pointer, this is the pointer. What is the address of num1, right? You want to put in a tab in there before we print out all this. So we want to copy all this and then paste it down here. So this is the address of num2 and p2 plus plus p2, right? So we run this and we have these addresses. So we'll go ahead, and now when we observe these, we have oxe up to d, right? All of this up to this point is the same as this address over here up to d. If you look carefully, the only difference is 34 and 38. So from this we can say that it was shifted to the right by 4 units because 34 plus 4 would give us 8 over here. And when we look at this, we used a long int. Over here, it's written 38. When we look at this, it's the same address up till the D. And when we compare it to after the addition or after the shift, is the same up till the D. So when we look at the last two digits, 38 and 40, we can see that that is equally 2 units to the right. So indeed there was a shift. Let's go ahead and run this to get the addresses again. Right, so these are in hexadecimal format. We can see that it's same up till the C and then same up till here as well. And the only difference is 8 and 4. And this is after the shift, so we can infer that it's by 4 units. And this one, it's not quite clear because it's 8 here and it's C8 here and it's D0 here. So I want us to get the intuition in the decimal format. So we'll go ahead and copy all of this. We close this and we want to paste it here as comments. Right. So then we want to convert the last two numbers or the last two inputs of this address, so C4 and C8. We want to convert it to a decimal format so that we can easily understand. So we'll see out DC and 0xC8. So this is the format to convert a hexadecimal number to a decimal number. So let me clear this thing up there. So hexadecimal to decimal. So then when we output this, that's for this one. And then we want to output the other one as well. So tab DEC and want to convert C4. Then after that, want to issue a new line. We copy this and we paste it down here and want to replace these with sorry. So this is C8 and this is C4. C8, C4. The next one is D0, D0 and C8, right? You might have wondered why I copied it and I'm doing this because when we run it, it's going to return a different address for each of these because the addresses are assigned on runtime. It's not assigned automatically by the C++ language. It's assigned on runtime by the computer system. So we are always going to get different addresses every time we run. That's why I copied this so that we can work with them and see what is really happening. Right, so let's add text to kind of clarify things on the screen when we are looking at it. So address of num1 and this is going to be num2. Basically they are not addresses, they are the shifts that we just want to compare. So I hope you guys will not forget that. So this is num2. Right, so I want to comment this out, or we can just run it so that you guys will see that it's not going to return the same address. Right, so we run this and we've got an error over here. What does it say? C4 was not declared. Okay, so C4 should be preceded by an OX and this as well by an OX, right? So now address of num1, after this we should issue a tab. Sorry about all of these errors. Right, we run this and now we can see that the addresses are different. Over here is ending in C4, over here is ending in 34. So we can see the difference over here. Now what I want you to realize is we copied the previous addresses from the run and we just converted the endings to decimal units so that we can kind of get the real shift. Now we can see the real shift from here. From 200, the original one was P1 and after the shift, sorry, the original was P1 which is 196 and after the shift it moved to 200 and that's for the integer data type. And we can see that it shifted by 4 units because 200 minus 196 is 4. For the long int, the previous P2 was 200 and the new P2 after the addition, which was this one D0, was 208. So we can see that it was shifted by 8 units. So why then did it shift by different units even though we added 1? That's the question we will be answering from this graphical representation. Now, as we have already talked about, the computer memory is in form of stacks in this order, sequentially arranged, and each of them is 1 byte each, right? So let's assume that this is the 300 stack on the computer memory, and this is 1 2 3 4 5 6 7 8 9 10 11, the 11th stack after the 300 one. Now we define two data types: int, let me write it over here, right? Int and then long int. As we have said, long int. These data types occupy different amount of spaces on the computer memory. For the sake of this example, let's say that integer data types store, or they occupy 2 bytes on the computer memory, and long ints occupy 4 bytes on the computer memory. So anytime you declare a long int, it's going to create a room of 4. And anytime you declare an int variable, is going to create a room of 2, right? So then let's see how many stacks the integer is going to store on the stack, on the memory stack. So I'll use a different color to represent that, right? So we have it occupying 2 bytes, so the computer creates 2 bytes for this particular variable, right? So that means that this particular variable, even though it will not occupy every space on this thing, on these two stacks, the computer has created it. Whether or not the variable occupies it or not is not the computer's business. So far as you have used an integer to declare that particular variable, it goes ahead to reserve that space. Whether you use it or not is not its business. And so this particular one occupies up to the 301st one, right? Now what happens for the long int? The long int reserves a room of 4. So let's say that this starts from here and here and here and here, right? So this is where this one will start, 306th stack up till 309 stack, right? So then when we add, so this was, let's say, P1, and this was where P2 is. So then P1 plus 1, where will it shift to? Will it shift to here, or will it shift to here? That's the question. When we run the computer to print out P1, it's going to print out this particular address. It's not going to print out, it's not going to print out this and this. It's just going to print out this. So basically it prints out where the variable starts storing from. So when you run to print out P2, when you print out cout P2, right, it's not going to print out this address. It's not going to print out this address. It's going to print out the first stack that the variable started storing from, and then counts the number of stacks that you have declared using this particular data type to the right. So when we say P1 plus 1, the computer shifts the memory address, the new memory address, to start from here. So P1 will then shift, and then this will be the new P1. So the new P1 will then start from here and occupy these two stacks. And for P2 plus 1, the original P2 ended over here. So when you add 1 to it, it's going to shift to this particular place. So the new P1, P2 would start from here and occupy 4 more stacks to the right. So this will be the new P2. So I hope you get the intuition over here. It's not immediately after the address, but then depending on the data type, it shifts by that amount of units depending on the data type, right? So I hope you get the intuition over here. So over here we saw that, let me run this and then we kind of explain again. So over here we saw that this one was shifted by 8 units and this was shifted by 4 units, right? So that is the basic intuition behind it. So go ahead and then we can use subtraction. I think it's just subtraction and then addition, shifting it to the right and to the left, right? So you can go ahead and then try out with any of these, and you can leave comments at the comment section of your output, right? So the next thing we want to look at is pointers and constants. So I'll go ahead and then